Oh, this is math class.
Okay.
Yeah, I know.
Calculator. No calculator.
You really, truly don't need one.
Does someone have an extra mechanical pencil?
What do you need, Julie? I got mechanical pencil.
Wait,
I just need a factor.
No. if I make this, you have to give me a high five.
Hey, I got you.
Oh, that was so close, literally on the rim. I really thought it was going
If it
in.
doesn't have, I'll let you know.
How about I give you a high five?
Mr. Ann, if I make this, you have to give me a high five.
Mr. Ann, is this your pencil?
No, you can have it. Okay, so what we're gonna do is we're gonna start by reviewing what a complex number is.
Sorry.
Z.
Okay, I'm ready.
So when we're talking about complex numbers, I like to use the variable z. Just like we use v for vector, we're gonna use z for complex number. Every complex number that we've been working with previously has two parts to it. It has my real part A, so this is a whole number that exists on my number line. And it has an imaginary part B, which is a whole number with an I attached to it.
Oh, no.
Okay, so we've dealt with complex numbers before. Today we're going to revisit them and look at them in the eyes of polar complex numbers.
Oh no,
Imaginary
is this the imaginary?
If we go ahead and designate our x-axis as our real axis and our y-axis as our imaginary axis, every complex number, a plus bi, can be rewritten as a rectangular coordinate AB. So every complex number can be rewritten as a coordinate AB.
So is this lesson gonna include graphing?
No.
Imagine.
Imaginary. Yes.
I
So
thought- I
since
thought
we
you meant
can
the word.
rewrite, these complex numbers as rectangular coordinates or vectors, we can actually perform operations with them. So we're going to do a brief review of operations of vectors and also do operations with complex numbers here.
What's that?
We did operations vectors.
Yes.
Oh,
I was like-
classes.
That was like last week.
So we're going to do two different operations with two different sets of numbers. We're going to start with vectors since we've done that before, and this is a nice little review.
I hate vectors.
If I am adding or subtracting two vectors together,
Oh, this stuff.
This stuff is easy. A1 plus B1.
yes. So if I'm adding or subtracting two vectors, A1, B1, and A2, B2,
Plus or minus.
Shoot.
plus and minus because it works the same for both, that simply means that I would add or subtract my like terms A and my like terms B to get whatever my new vector is. So we did this before with real numbers. It just says that I take my two A's, put them together, and my two B's, put them together, and rewrite my coordinate. We can also multiply a whole number into a vector. So for example, if I want to multiply C into vector AB, I just take C and multiply it into both parts of my vector individually, and then it creates my new vector.
Awesome.
So you just distribute.
Yes. We
Wait,
can,
This is review, correct?
yes, this is review. I can also square the magnitude of a given vector. And this comes out to be my A squared plus my B squared. Wow. So this is a nice little review. What we're going to do now is we're going to apply these same properties to complex numbers instead of vectors, but it's going to work the exact same way.
Is that literally it?
Well, this is part of it. Come on.
No, it's
Oh,
gonna take
no.
2
I'm making it silly.
at least.
You're a silly goose, Chandler.
So for complex numbers, I can add two complex numbers together. When I add them together, I add like parts together. So I add my two real parts together.
Number 5.
Plus my two imaginary parts together. Of course, we're going to do actual numerical examples of these, but these are just the general rules that they follow
Why does the I move to the outside?
because we always have the I at the end.
Is it B1I or B1?
B1I. That's B1I.
Okay.
Sounds like a new Star Wars character.
Again, I know it looks confusing. We are going to do numerical examples and it'll make more sense.
I gotta.
Just like with vectors, I can also multiply a number into a given complex number. And when I do, just like Jerry said, it distributes to each part of that complex number and creates a new one. So then this would become CA plus CB I.
Came right now.
Real.
The last part of this then is again the magnitude. This time we're taking the magnitude of a complex number and squaring it. And when I do, it comes out to be my real part squared plus my imaginary part squared. So we're going to do some examples of these.
I feel like my brain's lost.
Don't be lost or say you're lost until we do some examples.
The sad part is, we're doing math and there is not one number up there.
We're going to do them now. Actually, there's some little ones and twos.
Whoa. Magnitude. What happened to the I? Just disappeared.
Just wait.
That's because it's magnitude, buddy. Magnitude.
Examples.
Oh, shoot.
So the first one we're going to do is 3 plus 4i minus 2 plus i. So here I have two different complex numbers that I am subtracting. What is so funny?
Just digging for gold.
I was doing this and I was just like breathing.
Okay, so this is the first example we are starting with.
Just my tears thing. It was in my
Following the rule that we wrote down, when we combine two complex numbers with addition or subtraction, we apply that property or that operation to each of the like parts individually. So I'm first going to identify what my real parts are for each of these complex numbers.
It's 3 and 2.
In the first one, it's 3. In the second one, it's 2. So my new real part becomes 3 minus 2 because it was a subtraction operation.
Can we just do that?
Yes. Plus, then I'm going to do the same thing with my imaginary parts. My first imaginary part is 4. My second imaginary part is 1. So then I get 4 minus 1 with the I outside, and then I simplify it. 3 minus 2 becomes 1. 4 minus 1 becomes 3, and I have to keep the I on the end. So the subtraction of these two complex numbers simplifies into 1 plus 3i.
That's crazy. That's the one.
That would be your final answer.
So why?
This is easy.
I'm ready for
Right?
HW.
It looks scarier than it is.
Wait! I know
You'll
what
see.
Yeah,
I
you
know
got
what
us.
this is.
You got us.
Eventually, we're gonna go to where we have to multiply the I, and then it turns into an equation. I already know. I went through this in geometry.
Next one, just for
We
practice.
did it.
I know what she's on to. Yes, we did. Because the I's, remember, we have to multiply.
Hey, no spoilers.
Okay.
So for this example, I'm going to add two vectors together instead of two complex numbers, but the process is the same. I add like terms together and it creates my new vector. So what are my like terms here?
2, 6, 4, 1.
So we'll start with 2 and 6 because they're both the first coordinate of each of my vectors.
You scroll up.
The operation is addition, so I'm going to add them together. Then I'm going to do the same thing with my y coordinates, which are 4 and -1. And then I just simplify. So my new vector becomes 8, 3. Again, we've done this. This is not something new to you. I just figured I'd throw in a review. Questions so far?
Are we gonna have to do the I things like today?
Questions
tomorrow?
so far?
Yes. That was a question.
That's not a question I'm answering
About
right now.
what we've gone over.
Are we going to do this?
Is
What-
anybody confused by what we've covered thus far?
Absolutely not.
Are we okay? The
I'm-
only new part was adding and subtracting complex numbers. It's the only new part we've done.
I was
Oh,
confused.
Landon, you are.
Uh-oh.
What?
What happened?
I counted Landon absent.
Oh, yeah. I was. I,
I didn't say that. I said
shoot.
shoot.
I said.
Because usually it sits over there. I didn't say word.
She didn't even fit. It didn't even fit. She's like, I didn't say that.
She's like, I didn't
She
say
didn't
that,
even point out
buddy.
that.
It's okay.
I don't care.
I was
all good.
confused.
Yes.
So on the one before you had minus. So you had, like,
Seniors
Because it was
can't be
subtraction?
controlled.
but then you changed it.
Crazy.
So you're
That's
like, okay,
crazy
it's
animal.
subtraction.
Okay, I changed it because I subtracted the like terms.
Oh.
So that's where I applied the operation.
They just
We
put it
always
together.
assume that between the real and the complex is addition.
I just been puzzled on when you did the, like the 2 + 6, and like, why did you put them in the same?
Because those were both my first coordinates. Those were both my first coordinates. And these were both my second coordinates. That's how they
But
get
I'm
grouped.
asking, like, do they have, like,
They have to be grouped that way.
so they should be in one parenthesis together?
Yeah, because every vector has only one set of coordinates and our coordinates are always written in parentheses. Yes. Yes, ma'am.
Okay, I do it like differently though, but I still get the same outcome. I have to do it, I have to separate the parentheses, like I know
That's fine.
I have to do it because I get my commas confused.
No, you're fine.
Sit back.
You're fine. Okay. Any other questions thus far? Those are all good questions. So now we're gonna kind of switch gears a little bit and we're going to examine something that is specific to complex numbers. And that is called the conjugate of a complex number.
Oh, I
I
love
missed
this.
the conjugate so much.
So we're gonna
That was
start with the
best
fact that every complex number has a conjugate. And not conjugate.
Spellable leader.
And to denote that conjugate, we do the complex number variable z
Wait,
with a line over
I
it.
have a question.
What?
In Spellable, do you like?
That is not applicable.
No, do you get to write down the word, like, or do you just have to know it off the top of your head, or do they actually give you the chance to write down the word?
Oh,
Yeah, you have to write it. That's how they grade it.
Oh, that's how they. Okay.
That's how the proctor
I
grades
think
it.
I'd be better than you, to be honest.
Oh, that was a
Because I just spelled
challenge.
conjugate like.
Well, I can
No
spell it as well, but I mean,
Alright, do the hardest word you know.
the hardest one that I know.
Like, you write it down and then
Here
have
we
him
go,
write
so
it down.
wide.
Yeah, write it down.
When we get to the end, I will. Okay.
No one gets- Did anyone get the iridocyclitis?
You're a double like.
Thank you, Boone.
Okay. So what we're saying now is that every complex number z has a conjugate that is a z with a line over it. So anytime you see a line over the variable, that means conjugate.
Okay.
So when I'm talking about a conjugate, it means that the sign on the imaginary part changes. So if I have the complex number 1 minus 2i, its conjugate would be 1 plus 2i. So only the sign in the middle changes. Another example would be if I have -3 plus 4i as my complex number, then its conjugate would be -3 minus 4i.
Every time you say that, it reminds me of something.
What?
Conjugate.
Yeah,
Conjugate.
Conjugate.
Something also that's very cool about complex numbers is they don't necessarily have to have the real part to them. So I could have a complex number that is just 5i. It still has a conjugate, and the same rule still applies. So its conjugate would be -5i.
But see, for the -3, oh, it only switches to I.
It only changes the sign on the I.
Okay.
It
I'm over
only
it.
changes the sign on the I. Another really cool thing that happens when I have a conjugate and its original complex number is that if I were to multiply them together, it's going to come out to a whole real number. So, the product of a complex number and its conjugate can be expanded using FOIL,
Oh,
right?
foil.
So if I FOIL this out, a times a becomes a squared. A times negative bi becomes negative abi. A times bi becomes positive abi.
I love toilet.
And bi times negative bi becomes negative b squared I squared.
Is this still part of the conjugate?
Yes. So all I did was I FOILed them out.
Whoa, B squared.
What is the really, really cool thing that we see happening here when I FOILed them?
One of them
Yeah.
cancels.
Yeah.
The ABIs cancel. This is the reason that we use the conjugate. Because those cancel, leaving me just with a squared minus b squared I squared. So I know I promised you that the answer is just gonna be one whole real number. Right now, I still have an I squared in there though.
Get rid of that.
How do I get rid of that, Chandler?
Square root of I.
No.
Is it what I
You
was
can just
talking
drop it off,
about?
it's
It was,
imaginary.
no, you have to like multiply. There's like some way you do it. You
I didn't
put
do
it
that.
up front.
Jonah,
I know how to do it.
no.
Wait,
Devin,
let's teach.
Square the other
quick.
side.
I was always told to combine A and B and then put I in front.
You square root the whole thing.
Don't tell us anything unless it obviously gets out of
well, I have to tell you.
But
No,
I'm
never
gonna give
tell
you
me.
guys a couple more guesses.
I has a
Hold on,
number.
Steven.
Is I to the power of negative one?
I just want.
No, it's not.
What? I is negative one.
Getting closer, but no.
Negative 2.
Nope.
I is 0.
Say it again.
I,
No.
square root of negative one.
Okay, so I is equal to the square root of negative 1, which means I squared is equal to the square root of negative 1 squared, which equals what?
Negative
Negative
one.
Negative 1.
I knew I equaled negative.
So then to continue reducing this, I'm going to replace my I squared with negative 1. And when I do, I get a squared minus b squared times negative 1, which turns into a squared plus b squared. So that means my original complex number times its conjugate is equal to the magnitude squared. This is going to be very, very, very important to us because it's going to make my life so much easier when I'm solving division problems that involve complex numbers.
I remember this now.
I told you we did this.
So now what we're going to do is we're going to do an example that uses numbers so we can kind of show what's happening. And then we're going to do a division and then we're going to stop for the day.
I don't want to see our homework.
We're gonna do
Wait, we have homework for today, right? No.
You have homework that I assigned that will be due on Friday, yes. So let's do some actual numbers with this. So the example I would like to do is 2 minus 3i times 2 plus 3i.
It reminds me of the old days.
All right, let's try to do this one by ourselves.
Yes. You guys are going to FOIL this one out all by yourselves, and then we're going to see what it comes out to be in your heads.
Shut up.
Well, I already know these cancels, so.
Yeah.
I wasn't talking to
Gentlemen,
you.
ferme la bouche.
Huh?
Close your mouth.
Get out of the class.
title of this lesson.
Polar forms of complex numbers. Yes.
Good question.
We're supposed to get a whole number, correct?
You will get a nice, pretty whole number.
Is the answer?
Da-da-da.
Psych, I lied.
Okay. So this would be the only one that's squared, right? Not that.
What'd you forget?
That would be so-
You need a phone button.
No, I don't. Thanks though. I got the answer.
Wow.
Aren't you?
Hey, you didn't show your work. So
Hold on. So by the previous property, I know that it's gonna come out to equal 13. Because it is this squared plus that squared. 2 squared is 4, 3 squared is 9, 9 and 4 is 13. We are going to work through it to prove it. I know a lot of you already did it, but I'm gonna do it up here as well. But did you get it to come out to 13?
Yes.
So we know it's gonna work.
I'm still a foil.
I don't know how you are so smart.
Well, Jerry, you already know
Can
that.
I do that on the homework?
Yeah,
2 squared.
now that you know this, you don't have to go through the whole foiling process anymore. That's the whole reason I'm teaching this to you. Is so you don't have to spend that time that you could be doing something else. So of course, we're gonna prove that it works before I allow you to just shortcut it all the time. Yeah, we square this one and we square this one,
And then you get your answer.
and then you get your answer.
9.
Wait.
So let's prove that it
I have a
works.
question. Before we do this. So you obviously square both of these.
Yes,
And you take the opposite of the symbol inside of it?
it doesn't matter.
Doesn't matter. You just throw it together.
Do like a squared plus b squared.
Okay,
Because when I
every time.
square it, it's gonna turn positive anyway.
Okay.
Okay, let's FOIL. So 2 times 2 is 4.
False.
2 times 3i is 6i. Green. 2 times negative 3i is negative 6i. And negative 3i times 3i is negative 9i squared. These cancel, leaving me with 4 minus 9i squared. I squared equals negative 1. So this becomes 4 minus 9 times negative 1, which becomes 4 plus 9, which equals 13. So we have proven that it works. We've done an example that again proves that it works. So now if I ask you to multiply a complex number and its conjugate together, you don't have to FOIL it because you know the shortcut.
It works on everything, no matter.
Anytime you're multiplying a complex and its conjugate together, it'll work.
That's great. That's whack. I'm picking up what you're putting down.
Okay, so what we're gonna do now is we're going to apply this in a division problem.
Oof, okay.
I know, you're so excited. And then we are done for the day.
Easier.
I'm just kind of mad that like now she teaches us this all last semester.
Made you foil all of it.
I actually caught on to that and like so
I actually taught it in Algebra 2 last year.
Actually, Jenner, we know you're smart, so we go ahead.
I appreciate the compliment.
Does that only work with like 2, like?
The conjugate.
It only works with complex numbers. It actually technically also works if we have a whole number and a square root together in a denominator and we have to rationalize that, but it changes a little bit for that, but the concept still applies.
Nice.
So for here, it only works for complex numbers and its specific
Like
conjugate.
those.
Yeah.
Like if those two are in parentheses, would it work?
I'll show you in a second. Okay, so this is my problem. I gave you 4 plus 2i over 2 minus 3i. And I would like to simplify this.
20.
Simplifying it means I don't want a fraction anymore. I also don't want an imaginary part in my denominator because that's hideous and I don't like it. So the way that we ensure that an I will cancel from my denominator is what? Multiply by its conjugate. We've proven in the previous examples that when I multiply a complex number by its own conjugate, the i's are guaranteed to cancel, leaving just a nice, pretty whole number in the bottom. So that's what we're going to do. To not change the value of this fraction, I need to multiply that conjugate into the top and into the bottom. So I'm going to multiply the top and bottom by 2 plus 3i. And then I'm going to go ahead and multiply it all out. And that will give me my simplified number. This is half as much work now because I don't actually have to multiply this bottom out.
So multiply everything by
I have a
the
question.
denominator.
So, I understand. So 2 plus 3i is the conjugate.
My denominator, yes.
Oh, so we just take the conjugate of the denominator?
Yes.
Okay.
Yep, because that's the part I want to get rid of.
Wait a minute.
So,
Did you just do 4 squared plus 2 squared?
No, dude, no.
no.
4 squared, 9 squared.
Okay. The shortcut I showed you only works when multiplying a complex number and its own conjugate.
Oh,
So that
the bottom.
shortcut will work for the bottom. It won't work for the top because they are not conjugates of each other. So on the bottom, I know I'm going to get what?
13.
13, because 2 squared is 4, 3 squared is 9, 4 plus 9 is 13. So all I have to do now is FOIL out the top. Half as much work. So when I FOIL out the top, I get 8 plus 12i plus 4i plus 6i squared. I go ahead and combine my terms to simplify, and I get 8 plus 16i plus 6i squared over 13. I know I'm not finished because I still have an I squared in my numerator, so how do I simplify that out? I squared becomes -1, which means this +6 becomes a -6, and I can combine it with the 8 out front. And when I do, I get 2 plus 16i over 13. I will not leave it as a fraction because a complex number has 2 parts to it, so I will separate it into its 2 new fractions of 2 over 13 plus 16 over 13i. And then we are finished.
Plus 16 over.
13, yeah.
Not too bad.
I just take each of the tops and put it over the bottom. And then we're finished. So this is all that we are doing today. I wanted to break this up so you had time to process before we move into what we're doing tomorrow.
How many actual homework
Tomorrow's the
problems
bad
do
day.
you do?
I don't know, not a whole lot.
Like one?
Even on mine.
Not a whole lot. Tomorrow's the most fun.
Tomorrow's, oh,